Okay, this video is over the beginning of our Unit 8, but the goal is to teach you how to draw what's called a Lewis structure. So we're going to start looking at different kinds of bonding and what the molecules or the compounds actually look like. So earlier this year we studied the types of chemical bonding, ionic bonds, covalent bonds, and then we didn't really mention a whole lot of metallic bonds. But ionic bonds, what they're formed from is from a transfer of electrons. And so what we learned last unit is that the complete transfer of electrons happens when the atoms have large differences in their tendency to gain or lose electrons, so large differences in their electronegativities. Okay? And so one atom will completely take the electron away from the other. So then what happens and what makes them stick together is now you have a cation, which is positive, and an anion, which is negative. And now there's a Coulombic attraction between them. Okay, and so usually this happens between metals and nonmetals. And typically it's of the metals that are more reactive, group 1 and 2, and then the nonmetals that are also more reactive, groups 6 and 7. But it can happen with others. But what we're going to do this unit is more draw pictures instead of write sentences and explain them. And so when we draw ionic compounds, we generally show them in what is called a lattice structure. Okay? Because if you had, let's say we have a cation. I'm going to draw a couple of them. Okay, what a lattice structure is this red cation would be attracted to anions all around it. Negative anions would come and show an attraction in every direction. And I could draw this over and over and over and stack it over and over and over. But this is what's called a lattice structure. So they're not sharing electrons. They're just attracted to each other and stay near each other because of the opposite charges. What we studied in Unit 5 and 4 this year is for ionic compounds, a lot of times when you put them in water, a lot of them will dissolve, which means the ions will separate from each other or disassociate, because water is also attracted to these ions with its different polarities and will surround these ions. And so we do not draw these Lewis structures that we're going to learn this unit for ionic bonds. That's what we say an ionic bond looks like. It's this lattice. Okay, covalent bonds are when electrons are shared. And so this happens when the atoms involved have small differences in their electronegativity. Okay, so last unit we learned that difference is roughly between 0 to 1.7, with the 0 to 0.3 being a nonpolar covalent, and then the 0.3 to 1.7 was a polar covalent. And so these usually happen between non-metal atoms. So a nonmetal and a nonmetal. These are the ones that we're going to have to draw the sharing. These are what we're going to draw Lewis structures for. Okay, so that's what we're going to learn this unit, is how to draw and describe how they're sharing electrons. Okay, the last one we're not going to spend much time on in this unit at all. Metallic bonds are formed when multiple metals get together. So it could be the same metal repeatedly, or it could be different metals, but they're all metal atoms. And so what we say, and there's a lot deeper level to this, but what we say is that they all collectively pool their valence electrons into a sea of electrons that's able to flow between them. And so that's where we get that metals conduct electricity very well, is that the electrons are able to move. Ionic bonds do not conduct electricity very well when they're in the solid state, like this, because the electrons aren't free to move. They're all very stuck and localized. Covalent bonds, same way. They're localized between two atoms. But electrons in a metallic bond, they're delocalized. They're not specific to one area, and they're able to move freely. Okay? So if we were drawing a metallic bond, a lot of times it's going to end up looking like similar to an ionic, where they're stacked over and over and over next to each other, because they're pooling their electrons in a C between them. So the electrons are free to flow in between them. And so I drew the same kind of atom over and over and over. That would be the same metal. So let's say it's an iron sample or a copper sample. So there are also metals that are not on our periodic table that are mixtures, like bronze and brass, that are mixtures of multiple metals, and those are called alloys. So for an alloy, maybe one of these would be different. Okay, and there's different kinds of alloys that you'll learn in a higher level chemistry, because you also have alloys where the different metal fits in between these little gaps. Okay, and those are not ionic. This is still considered metallic because they're all metals. They're not transferring electrons. They're all pooling them together. Okay, so we're going to study this unit, covalent bonds. That's what we're going to look at. So we're going to start looking at what a Lewis structure is and how to build them. So first up, what we've got are called Lewis dot symbols. So these are for individual atoms. Nobody's bonded yet. How do you draw how they're going to maybe connect and bond and all that kind of stuff? So it's a shorthand way of depicting this with a picture instead of writing out our electron configurations. But it only ever draws the valence electrons. These are the ones that are going to be involved in any kind of bonding, connections between atoms. Okay, and so what we do to draw this is we take the element, let's say lithium, and we look at its electrons, and we only look at the valence. So for lithium, the valence would only be in energy level number 2. Okay, and it's got one electron in energy level number 2. So when we draw this Lewis symbol, we draw the lithium symbol for the Li, and then we draw a single dot. Each dot is going to represent one electron. So we draw one dot, and it doesn't matter which side it's on, but one dot, and that's lithium symbol. So we proceed through, I have shown the 8 elements in period number 2, and seeing what happens to their valence electrons. So I've listed their valence electrons. And so one nice thing about how the periodic table is arranged, if we look at this, we're going to be able to want to count their valence electrons a little quicker than writing out their electron configurations, even they're condensed. And so if you look at their valence electron, the number of valence electrons, for lithium we've got 1, beryllium we've got 2, boron we've got 3, carbon we've got 4, nitrogen we have 5, oxygen we have 6, fluorine we have 7, and helium we have 8. If you look at the A group number, okay, not the 13, 14 situation, but the A group number. The A group number for the main groups, the A groups, gives the valence electrons. So when we go look up carbon, right here, if we wrote the full electron configuration, we'd say, hey, we have 2s2, 2p2 as our valence. That's 4 electrons. But if we go find carbon on the periodic table, it's sitting in group 4a. It has 4 valence electrons. So this is a way that you can find the valence very, very quickly without doing anything. And it's a nice little advantage of our organization. So if I ask you about bromine, you don't have to go list out the full electron configuration to know that it has 7 valence electrons. And so for these Lewis structures, we're only going to end up using their valence. So that's all you're going to have to care about. And so a little note for you on this, it said, hey, the A group number gives the valence electrons. And so when there's more than one valence electron, other than lithium, we're just going to move the dots and place them on the 4 sides of the symbol. And we're going to keep them unpaired as long as possible and then pair them up as we need to. So the most valence electrons anyone will have is 8, which gives us 2 on each side. Okay, and so you can see the symbols here. For beryllium, we put 2 on different sides. Then boron, we have 3 different sides. And carbon, we have 4 different sides. And then nitrogen, when we hit 5, we have to pair something up. Oxygen, we have to pair 2 up. Fluorine, we have to pair 3 up. And then neon has everybody paired. Okay, so those are Lewis dot symbols. Those are for individual atoms. So if you were looking at bromine, bromine would have 7 valence electrons, just like fluorine. Its structure, its Lewis structure, would look just like fluorine's. Its Lewis dot symbol. Okay, so we're going to practice a couple of these to see if we can draw them. So we've already looked at lithium, but seeing if we can look at the periodic table. So I can bring this in a little bit to help us out. Okay, so lithium, we just simply draw the symbol, and we have 1 valence electron. So for calcium, We go find calcium on the periodic table. Calcium has 2 valence electrons, so we pick 2 sides to put that. Doesn't matter which sides. Okay, for phosphorus, we go find phosphorus on the periodic table, and it's going to have 5 valence electrons. So we go 1, 2, 3, 4, and 5. At least one of them has to be paired up. Okay, I just did bromine, but we'll go through bromine again. So bromine has 7 valence electrons. So we go 1, 2, 3, 4, 5, 6, 7. And then iodine, if we go find iodine, iodine is in the same group, same family as bromine. It's going to have the same valence electrons. And that's why we call them groups or families, because they're going to end up behaving the same because of these valence electrons. So notice I drew a different one paired than I did for bromine. It does not matter. Okay, we're just depicting for ourselves where things are and locating them as a shorthand notation. Okay, and then last up is carbon. So carbon has 4 valence electrons. So we have 1, 2, 3, and 4. Okay, so the idea with these is now we're going to try to figure out how these things might share with other atoms and make these covalent bonds. And so what covalent bonds are sharing, and what we found, and there are always exceptions, but what we found is that elements will typically share until they've reached a full valence shell. Okay, and so just to give you an example, one, this is going to get a little large fast, okay, is let's say carbon and bromine were involved. Okay, well, you can see right now that bromine doesn't have a full valence shell. It is one short of that. It has 7 in its valence. It ends in 2p5, and it can fit 2p6. Carbon ends in 2p2 and can go all the way to 2p6. So carbon has 4 spots to bond. Okay, and so what can happen to make a covalent bond is that these two can get close together, and these valence electrons can actually overlap and be shared between those two. So what I just drew, what I highlighted in yellow, is what we call a covalent bond, is when the two atoms are sharing a pair of electrons. Okay, sharing some electrons between their nuclei. They're both pulling on them, and it's a tug of war between the two, but they're both sharing them. Okay, and from what you can see right now, doing that allows bromine to have a completely full valence shell. Now it's at 4p6, and it's full. And so then bromine is not going to try to share anymore. Carbon now would only have 5 in its valence shell. It's sharing one of bromine's. That's still not full. So what carbon can do is carbon can actually connect to multiple other atoms in multiple other ways and share multiple times. So let's say there was a hydrogen over here, and hydrogen has 1 valence electron. So carbon could share with hydrogen that way and have another covalent bond. Okay, and again, it could repeat the process 2 more times, and there's other things it can do, but 2 more times until it fills up its valence shell. And so maybe in biology you learned how important carbon is to us, but carbon can connect lots of different ways and bond lots of different ways because it has four available spaces in its valence shell. And so carbon makes all kinds of interesting structures that make up all of our organic molecules that are so important to our existence. Okay, so that's what we're going to look at, is drawing these symbols as connections. So what a covalent bond, there's lots of vocab on this sheet. A covalent bond is simply the mutual attraction between the nuclei and a pair of electrons between 2 atoms. So both atoms, like I drew the carbon and the bromine, these symbols are going to represent our nuclei, and then the electrons are what we draw as the dots. And so what we did when I showed them sharing a pair, okay, and I know I didn't draw all the electrons, but that would be the mutual attraction. Both nuclei are attracted to that pair of electrons. So the pair of electrons that is actually shared between the atoms is called a shared or bonding pair. So that highlighted yellow is the bonding pair. So when we drew bromine before, we also had bromine have 6 other electrons out here that weren't involved in that pair. So any electron pairs that are part of the valence shell but not involved in bonding, those are called lone pairs or unshared pairs. Okay? So these next three things won't really make any sense to you until we start drawing multiple structures. But bond order is how many pairs are shared between any two bonded atoms. So right now, what you can see for the thing that I drew, that's all you're going to be able to see is this first one. There is just one pair shared between the carbon and the bromine. And so that is what's called a single bond. Just one pair of electrons. So it's a single bond. And for bond order, what we say is it has a bond order of 1. These are the most common type of bonds, but we just say we have one pair. So there's a possibility of things that we're sharing 2 pairs between 2 atoms, or 3 pairs, which we call double or triple bonds, which we'll look at in a little bit. So we're going to try to draw these. So Lewis structures are what we're going to build, and they're 2-dimensional. That's important because we're going to work on 3D at the end of this unit. 2-dimensional structures that show all the electron dots that show how the things are connected to each other. It just shows the connections. It doesn't show how it exists 3-dimensionally, like its shape and all that kind of stuff, which is really important. Okay, so there are sets of directions for how you draw these Lewis structures. So you're going to want to be able to go back through them. I'm not going to read them at you, but I'm going to talk you through as I build several of them what these rules are. So you can go back and listen maybe as you're reading these and why I picked certain things. Okay. So there are definitely exceptions that we're going to look at, but we're just going to start drawing them. Okay, so what you do when you draw these Lewis structures is you have to have the chemical formula for the compound. Okay, so I'm going to start with methane, which I'm going to give you as CH4. So the very first thing that you want to do, the most important thing you can do when you're drawing these, is count the total number of electrons that you should draw before you start. So how you do that is you look up each element and you go look up how many valence electrons it has. So carbon has 4 valence electrons. So I've got 1 carbon in my structure. I'm going to have 4 electrons from carbon. Then I'm going to go look up hydrogen, and hydrogen has 1 valence electron. However, I have 4 hydrogens. So there's going to be 4 of those little ones, and I'm going to add these together to get my total number of electrons. So that's most important to me first. I have to know how many electrons, how many dots I'm drawing in my structure. If I don't have that number right, my structure is not going to be right. So then what you're going to do is you're going to draw what's called a skeleton and for the structure. And so what that means is you're going to put all the element symbols where you think they're going to go. And this may take some erasing, but there's a set of things that you can go through to decide how the skeleton is going to exist. So for the ones we're going to draw, there are lots more complicated ones, but the ones we're going to draw are going to have a central atom and then surrounding atoms. And so you need to choose the central atom. So a couple things for you on the central atom. Usually the central atom is the one that occurs least in the chemical formula. So carbon only appears once. It's going to be the one that occurs least there. Hydrogen occurs 4 times. The other thing is if carbon is involved in the chemical formula, carbon is almost always in the middle. What we looked at before was carbon has so many places to share different electrons because it can fit 4 more in its valence shell that it generally is in the middle. Okay, so we're going to put carbon in the middle. Once you decide who's in the middle, all of the other atoms are going to surround it. So it does not matter that I did these symmetrically nice and around. That has no meaning. Okay, it's nice for me to help space. If I wanted to put all 4 hydrogens up here, I could. It's not pretty and it's going to be harder for me to draw, but I could. So these are 2-dimensional structures. We will learn later this unit how these things actually exist in 3D. So these give you no idea of how it actually is shaped in nature. All it gives you is who's connected to who and how. Okay, and so once you decide on a skeleton, then you're going to go place all of these electrons. And so how you decide to place them is the first thing you're going to do is connect every outside atom in the skeleton to the central using 2 electrons. So we're going to use 2 dots. So 2 dots, 2 dots, 2 dots, 2 dots. So you notice sometimes I pointed them different directions. It does not matter. Now I'm actually going to change the one on the left because I know what I'm going to use as a shortcut, but it does not matter how you draw these, whether they're up and down or sideways, whatever. We're just accounting for them. So I drew 1, 2, 3, 4, 5, 6, 7, 8. Well, that's all of my electrons. So I'm out. I can't draw any more. Okay, so the next sets of the rules are not relevant for this structure. So then the last thing you need to do once you're out of electrons is you need to go assess your diagram. And so you need to look at every element in there and see how many electrons it would have based on now the sharing, and see if its valence is now full. And so for hydrogen, what that means is I'm going to circle little hydrogens. Hydrogen is sharing electrons with my drawing with carbon here. Each of these hydrogens is sharing 2 electrons with carbon. Okay? And then carbon is sharing in all 4 directions, so carbon is sharing that way. So what I just drew inside the different colors are what would be the valence shells of each of the atoms. So if you look at each of the hydrogens, they have 2 electrons in them. Well, if you go look up hydrogen, hydrogen is an energy level number 1, and it's usually 1s1, showing 1 electron. Well, full energy level number 1, a full valence shell, would be 1s2. So hydrogen only has can only max out at 2 electrons. Well, each of these hydrogens has 2 electrons in its valence shell now. It's maxed out. Carbon is an energy level number 2, and its valence is 2s2, 2p2, but it could go all the way up to being full to 2p6. So it can end up with a total of 8. And a lot of atoms are going to total out at 8, going back to that octet that we talked about last unit. And so if you look at what's in carbon's little valence shell that I circled in green, you have 8 pink dots. That's a full valence shell. So this is the structure for methane. Okay? So you want to look at that. You don't necessarily have to circle them, but you definitely want to assess that, because we're going to have some diagrams that we're going to have to alter. Okay? The other thing that you can do on these, that you may have seen structures that look slightly different, is that drawing dots, 8 of them is not bad, but when you have to draw 40, it can be a little tedious. So we've come up with a system to represent some dots, that any 2 dots can be connected with a single line, and you can draw your Lewis structure so that a line is equivalent to 2 dots. Okay? And it is up to you whether you want to use dots, whether you want to use lines, or whether you want to use a combination. I typically end up using a combination based on what I know is happening later this unit and what we need to focus on, because dots are easier to see sometimes, but lines are faster to draw. And so I focus some things on dots and some things on lines, but that takes practice and knowing what you're looking for. So I will show you that as we move through this unit. Okay, so you may have seen structures in biology drawn with all these lines connecting things. Those represented covalent bonds. Okay, so this is what's called a single bond, because it has 1 pair of electrons shared between 2 atoms. These are all single bonds. Okay, so carbon has 4 single bonds here. All right, so the next structure, we're going to go phosphorus trichloride. So we have to have the formula. So these are all covalent, which means that we're going to use prefixes with the names, which is nice. Okay, so phosphorus trichloride, 1 phosphorus, 3 chlorines. Most important thing we can do is count the total number of valence. Okay, so we're going to go find phosphorus on the periodic table, and we're going to go see how many valence. It has 5. We're going to go find chlorine, and it has 7, but there are 3 of them. So we're going to multiply that 7 by 3. So total I have 5 plus 21. I have 26 electrons that I get to draw. You need to decide that first. Okay? So then the second step is I'm going to draw the skeleton. So no carbon in the structure, but I'm going to choose the element that occurs least frequently in that formula as my central atom. And then I'm going to surround it with chlorines. It doesn't matter which side you use. I picked those 3 and I separated them. So I have 26 electrons. So first up, I'm going to connect them all to the middle. So I've got 1, 2, 3, 4, 5, 6. I still have 20 more to place. And so the next thing that you're going to do is you're going to go around the outer atoms. You've got to start with the outer atoms, and you're going to fill their valence shells up. So for most atoms, that means just go to 8. 8 is usually the valence shell because S2, P6. So I'm going to focus on the chlorine on the right. So the chlorine on the right currently has 2 electrons in its valence shell right now with my picture. So I'm going to make that go to 8. Okay, so I'm going to put 3, 4, 5, 6, 7, 8. Okay, and that would be my valence shell for chlorine is now full at 8. So now I've given up 12 or placed 12 electrons. I still have 14 more. So I'm going to repeat that process for all the other chlorines. Okay, and I'm just going to draw these green circles in. You won't need to be doing these, but to help me know when I'm full to show you. So this is, now I've got 18 electrons. I drew another 6. And then I've got 20, 22, 24. So now all my chlorines have 8. They're full. And I still have 2 electrons. So once you're full with the outside, only until the outside is full, then you come to the middle atom and you dump whatever electrons are left on that middle atom. So 25 and 26. Okay? So then you assess, you go back to your drawing and you assess. Well, my chlorines, I knew that I filled those up. So then I look at my phosphorus in the middle and I say, okay, is that a full valence shell? So if you look at what's inside the blue little blob now, I have 8 electrons in there. That's a full shell for phosphorus. So that's my structure. This is what I'm going to end with. So again, you can also see, I'm going to draw it down, or I'm going to connect them a little different. You may see this structure drawn with all lines instead of all dots. Okay, you should put a set of lines up there. That's a fine structure and much faster. You just have to remember that each line is 2 dots. Okay, I tend to drew everything as lines except for the pair of electrons that are sitting, any pairs of electrons that are sitting on that middle atom, because those are going to become important later. Okay, so these things right here that I just drew that are connected, those are single bonds. Those are one pair of electrons in between those atoms. The atoms, the atoms that or the electrons, sorry, that I'm highlighting in yellow, all of the electrons that I highlighted in yellow, those are called lone pairs or non-bonding pairs. So we don't say that those are bonds or anything like that because they belong only to one atom. So there's 3 single bonds here. There's only 6 electrons total that are shared, and everything else belongs only to one atom. Okay. So then we're going to go to phosphorus pentachloride. Okay. So that's 5 chlorines. So first up, most important thing is counting electrons. So phosphorus, just like PCl3, phosphorus has 5. Chlorine has 7 still, but now we have 5 of them. So now I have 40 electrons that I have to draw. So I'm going to, again, decide on a central atom. It's going to be phosphorus for me. Okay, and I'm going to surround it with chlorines. Alright, so I've got 40 electrons. So I'm going to do it with lines this time, just to show you counting off a little bit faster. Right off the bat. So I'm going to go 2, 4, 6, 8, 10. So that's my first 10 electrons that connects everybody. I still have 30 more electrons. So then I go to the outer atoms and I fill them up. So I'm at 10. So here goes 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay? And I'm out. I'm out of electrons. So I don't have to dump anything on the middle. So then the last step is to go back and assess my drawing. So I just filled up all those chlorines, so those chlorines should be good. All of those chlorines in their valence have 8. But something weird happens here. If I look at phosphorus in that little pink realm, I have 10 electrons shown. 5 pairs of that, 5 of those lines which each represent 2. So I have 10 electrons. That's more than 8. So I have to ask myself, is this okay? So I just told you for most atoms it's going to be 8. Is it okay to put 10 electrons in there? And yes, it is. This is a real thing that happens in nature. And if you look at B and C, the formulas, PCl3 had phosphorus end with 8, and PCl5 had phosphorus end with 10. And they're real chemicals. So we can't argue with nature. We have to figure out why this is able to happen. And so phosphorus is right here. And it would have the electron configuration of neon and then 3s2, 3p3. And so what we would think is a full valence shell. We would add 3 more electrons and we go to 3p6. And that would max out at 8, and that's what PCl3 did. However, PCl5 had 10, and there's no more, we can't put any more electrons in that p orbital, but you do have to remember something that happens and starts first in energy level number 3 is that there's also a 3d orbital here with no electrons in it. We usually don't start filling it until we get to these atoms. But the idea is, as long as you are in the third energy level, at least the third energy level, you have d orbitals available. Whether they're full or not is a different thing, but they are space for you to put electrons. And so what phosphorus does in PCl5 is it crams an extra 2 electrons into that orbital and has 3d2 up there, and that's okay. There's space for it, okay, for it to go over 8. So you don't have to learn, like you don't have to know where those go or anything like that. What you have to know is that once you get to energy level number 3, that is the first level that has d orbitals, 3d is our first d orbital, that you can cram more than 8. So nitrogen could not do this same thing that phosphorus does because it only has 2 energy levels and there's no d orbital. There's no empty space for it to fill. Okay, so this is an okay structure. So our last one for right now is water. This one you should have seen a bunch in different ways, but we've got H2O. So we're going to count valence electrons. So hydrogen has 1, but there's 2 hydrogens. And oxygen has 6. So we have a total of 8 electrons. So we're going to pick a middle atom. So oxygen occurs least frequently. We're going to put oxygen in the middle. We're going to put hydrogen on the outside. So it doesn't matter if you put them top and bottom, if you put them directly left and right, it does not matter. I'm in the tendency of drawing it this way because I know it's coming and the structure of it, but it does not matter. Okay, so I'm going to connect my atoms. So I've got 2, 4. Okay, and then I have 4 more electrons, I'm supposed to go around the outside atoms and fill those up. But hydrogen, as we talked about already, hydrogen only has 1 energy level. It's full at 2 electrons. You will never dump any more electrons on hydrogen. And so I've got 4 more electrons, and where they have to get dumped is on the central atom, on the oxygen. So I've got 4 more electrons. I'm going to have 2 pairs up there. Okay, and so then if I go back and assess my drawing, I know my hydrogens are good, and I look at my oxygen, okay, and now I have 8 electrons in the oxygen's valence shell, so oxygen is good. So this is the structure you'll see for water, and a lot of times earlier this year we drew it as something that looked like this little Mickey Mouse. That was the oxygen and the little hydrogens. Okay, the reason it's shaped like this, with these hydrogens pointed like that, is because of these lone pairs of electrons. Okay, so there are more structures that we'll draw that get a little more complicated, but that's an introduction.